Hi, everybody. It's Professor Mitchell. Today we are finishing up Chapter 3, talking about confidence intervals for a population proportion. And here is your standard disclaimer. All right. So the objectives in this section are to find the confidence interval given a population proportion and calculate the sample size required to estimate a population proportion with a given confidence level. So to review, this part is pretty much the same as what you've heard in previous videos. The confidence level, CL, is the area in the middle of the standard normal distribution. So this would be similar to part 1 of chapter 8. CL is denoted 1 minus alpha, which means, so here is the area 1 minus alpha. Alpha is the non-shaded area that's split equally between the two tails. So each tail contains an area equal to alpha over 2. And remember that the z-score that has an area to the right of alpha over 2 is denoted by z sub alpha over 2. So this is the z-score we need for calculating a confidence interval. So here are some of the most common confidence levels and their corresponding z-scores. You would use, let's see, so the number attached to z is alpha over 2, so this would be for an 80% confidence interval. The area in each tail is 0.1, which means the area in the middle is 0.8. So that's 80%, this would be 90%, 95%, 98%, and 99%. The sample proportion is calculated like this. It's denoted P prime by your book. And you just do X divided by N, where X is the number of elements in the sample that have the desired property, divided by the total number in the sample. And then Q prime is just 1 minus P prime. The error bound, which in this section is denoted EBP for error bound for a proportion, is calculated with a z-score. And here is the formula that we use to calculate the error bound. The error bound for a proportion is equal to z sub alpha over 2 times the square root of P prime Q prime divided by N. So using the sample proportion as the point estimate and the error bound for the proportion as the margin of error, the confidence interval at a confidence level alpha can be written like this: P prime plus or minus EBP. And the interpretation would have this format: with given degree or given percent confidence, the population proportion of whatever is being described in the problem is between some percent and some other percent. So obviously we will see examples of that coming up right now. So Professor King wants to gauge how many students passed his final exam. Students can either score a pass or fail on the exam. He randomly selects 100 exams and finds 73 students that passed. What is the 95% confidence interval for the population proportion of Professor King's students who passed their final exams? So they've given me the table here. Before I go on, this is a 95% confidence interval, which means 95% in the middle. That means 5% outside. So the area in each tail is 2.5%. So we're going to use this z-score right here, 1.96, and that's going to look like this. P prime is 73 out of 100. 73 students in the sample passed out of 100 students in the sample. So that's 0.73, which means Q prime is 1 minus 0.73, which is 0.27. So the error bound is going to be z sub 0.025 times the square root of P prime Q prime divided by N. Hopefully you've got your calculator handy, because I would like you to try this and make sure that you get the same answer. 1.96 times the square root of 0.73 times 0.27 divided by 100. Make sure this entire fraction is under the square root. And if you do it correctly, it should come out to 0.087. I'm just going to check that myself really quick, because it has happened that I have found mistakes in here, but that does seem to be correct. So the error bound is 0.087, 8.7%. So the confidence interval is going to be P prime plus or minus the error bound. Remember to put the smaller number first when you write it in interval notation. 0.73 minus 0.087 up to 0.73 plus 0.087 gives me a confidence interval from 0.643 to 0.817. So the interpretation is, with 95% confidence, the population proportion for Professor King's students who pass their final exams is between 64.3% and 81.7%. So I just want to mention before we go on, you want to be really careful about rounding, especially in this section. I would suggest that all these decimals, while you're doing the problem, keep at least 4 decimal places, if not more. Okay, so here's one that you can try. Pause the video and try this one. Very, very similar. Professor King wants to gauge how many students passed his final exam. Students can score either a pass or a fail. He randomly selects 80 exams and finds 67 students that passed. What is the 90% confidence interval for the population proportion of Professor King's students who passed their final exams? So in this problem, P prime is 67 out of 80, which is 0.8375. That means Q prime is 1 minus 0.8375, which is 0.1625. So the error bound is Z sub 0.05. This is a 90% confidence interval, which means 90% in the middle. That means 5% in each tail. So the Z-score that corresponds with that is 1.645 times the square root of 0.8375 times 0.1625 divided by 80. And that comes out to 0.0678. And you should check that. Hopefully you've already done this problem. So the confidence interval, is P prime plus or minus the error bound. So 0.8375 minus 0.0678, 0.8375 plus 0.0678 gives me the interval from 0.77 to 0.905. And I was just looking ahead and I noticed a little typo. Uh-oh. Well, let's see if we can do it like this. No, I don't think that's going to work. Okay, just had to fix a typo in the interpretation. That still said 95%. Must have been a holdover from the last example. So with 90% confidence, the population proportion for Professor King's students who pass their final exams is between 77% and 90.5%. So now we move on to finding desired sample size or required sample size if you want a specific margin of error. So let's say, for example, that this margin of error, 6.8%, was too big. And Professor King decided that he wanted the margin of error to be no more than, let's say, 4%. What he would have to do would be to make the sample size larger. So this formula will tell you how large the sample has to be. If researchers desire a specific margin of error, they can use the error-bound formula to calculate the required sample size in order to get that error. So how you do that is you take the error-bound formula that we were just working with, and you solve it for n. And when you solve it for n, what you get is n equals z squared times p prime q prime divided by the required error bound squared. Okay, now frequently it does happen that there is no preliminary information on what the sample proportion is, and that's because I'm trying to decide how large should the sample be. So that suggests that I don't have a sample proportion, okay? So if there's no preliminary information available on the sample proportion, just assume that P prime and Q prime, are both 0.5. That is a worst case scenario, and that will make this required sample size as large as it can possibly be. But there are ways to get a preliminary sample size. You could, for example, just collect a sample of any size and see what the sample proportion is for that sample, and then use that for P prime. In both of these examples, though, we're going to use 0.5 for P prime. And remember, just like in previous sections, that if the calculated sample size is not an exact whole number, the sample size still has to be a whole number. Always round that up. All right, so if it says the required sample size must be at least 240.2, normally you think of rounding 240.2 down, but if it says at least 240.2, 240 wouldn't do that. So you want to always round it up. All right, so here's an example. Suppose a phone company wants to determine the current percentage of senior customers who use text messaging. How many senior customers should the company survey in order to be 95% confident that the estimated proportion is within 2 percentage points of the true population proportion of senior customers who actually use text messaging? So here's our formula, z squared times p prime q prime divided by required error bound squared. Because we're doing a 95% confidence interval, we would use 1.96 for z. And because we're not given any information on the sample proportion, we're going to use 0.5 for both p prime and q prime. And then we want the estimated proportion to be within 2% of the true proportion, so that makes the error bound 0.02. And when you crunch these numbers, which you should try, hopefully you still got your calculator handy, that comes out to 2,401 seniors must be surveyed. So that's quite a few. Okay, here's one that you should pause the video and try. It's very similar. Suppose a phone company wants to determine the current percentage of senior customers who use text messaging. How many senior customers should the company survey in order to be 90% confident that the estimated sample proportion is within 4 percentage points of the true population proportion of senior customers who use text messaging? So using the same formula, now we're doing a 90% confidence interval. So the z-score that corresponds to 90% confidence is 1.645. Again, we have no preliminary information on the sample proportion, so we use 0.5 for both p prime and q prime. And this time the required error bound is 0.04. So when we crunch those numbers, we get that about 386 seniors should be surveyed. And I'm just checking. Okay, well, I'm glad I was paying attention. Oh, they're killing me with their typos. I really need to start checking these more carefully before I make the video. So 0.6765 divided by 0.0016 does not come out to the number that they had there originally. It actually comes out to about 422.8, which we would round up, not because it's a 0.8, but because you always, always, always round up. Even if it had been a 0.1, I would have rounded it up. So at least 423 seniors should be surveyed in order to get a 90% confidence interval that gives me a population proportion within 4 percentage points of my sample proportion. And that concludes Chapter 8.